Hi everybody, Physics Ninja here. Welcome to my video on power and LRC circuits. In the previous video, I looked at LRC circuits in detail. I showed you how to calculate maximum current, the phase, and the voltage across all the elements, right? We reviewed basic AC circuits. In this case, what we want to do is focus on power. What are the properties of power that we're interested in? Well, how do you calculate, for example, the average power being supplied by the AC generator? How do we calculate a power factor for an AC circuit like this? How do we plot power resonant curves and what are their properties? How are their properties, for example, the peak of the curve and the full width at half maximum of the curve? How do we define those things? How do we calculate quantities associated with those curves? In the last part of the video, we'll look at something called a quality factor, the Q factor for a harmonic oscillator. How does it apply to an LRC circuit like this? I'll show you how to calculate it. A little bit of algebra, but that's life. All right, like with all my videos, if you like it, give it a thumbs up. Consider subscribing to Physics Ninja. It is the best way to support what I do. All right, let's get started. All right, so we start off with our series RLC circuit right here, and remember some definitions here. We had the tangent of the angle delta, and the maximum current were given by these two expressions over here, like we did in the previous video. Now remember, my applied voltage here, that's from the AC generator, is simply written like this, as an amplitude of Vmax, and has a time dependence that looks like cos of omega t. We solve this Imax current by imposing a current that was written like this form here. It had an amplitude equal to Imax, and again, it had the same angular frequency omega, but we had this additional factor here inside this phase, and that was just something we call the phase angle. So depending on the values of L and C, we could have a phase shift between the voltage and the current in this circuit. So that was important definitions over here. Now here we're interested in power. So we're going to start off with instantaneous power. Again, I could look at, for example, how much power is delivered by the source. If you remember the definition for power, it's simply voltage times the current. Or I could look at, for example, how much power is being dissipated by this resistor. These are kind of two standard definitions here for looking at power. The first one, power delivered by the source. Our second is power being dissipated by that resistance, is R multiplied by the current squared flowing through that resistor. All right, so let's first start off with P of T right here. And now we'll simply substitute our two equations here for the applied voltage and the current. Pretty straightforward. All right, so you get this expression here. I've just brought out the Vmax and the Imax to the front. And now you look at, we have two terms that have cos of omega t. However, one of them, again, has a phase shift depending on the values of inductance and capacitance in the circuit. So my goal now is to look at what is the average power being delivered by this AC generator. So the definition of an average, this is instantaneous, right? If you want to average out a quantity, what you have to do is you have to take all the values and divide it by the total number of values, right? You add them up. In terms of calculus, this is what it looks like. So I have to integrate this instantaneous power here over time, and I am integrating over one complete cycle. Uppercase T here is nothing more than the period of oscillation of this AC signal. And in the front, you just have also this 1 over T factor that appears. So now what you do is you take my expression for that instantaneous power and I simply substitute it in right here into this expression. So this is going to be a long, messy expression, but no problem. You just substitute that in there. And now we're left with taking out the constant terms, bringing them outside of the integral. That's what I've done over here with Vmax and Imax. And now I'm left to evaluate this integral over here between those limits of integration. All right, so here's my expression. My goal is to evaluate this term right here. Now this one here could be a little bit tricky if you are not very strong in calculus, but one of the easiest approaches here is to try to convert this multiplication of two trig functions into the sum of two trig functions, which is easier to integrate. And in order to do that, I'm just going to use a trigonometric identity, and one of them involves two angles like this. If I multiply cosine of some angle A multiplied by cosine of the angle B, I can write that in terms of the summation of two terms. And one of them involves the difference between those two angles, and one of them is the sum of the two angles. So now instead of using A and B, what I use now is omega t, and I use omega t minus delta right here as A and B. So you substitute simply A as omega t and B as omega t minus delta. You substitute that into the trigonometric identity, and there is an important thing that happens over here. First of all, well, you get cancellations of omega t for one of the terms, and for the other term they add together. All right, so now we can go back and substitute this entire thing back into the integral, because that was the whole goal of doing this trig identity substitution. All right, this looks very, very messy. However, it is okay. Let's look at the first term. The first term here does not depend on time, right? So that's just simply cos of delta. Our second term, actually, I'm going to leave that to you, but if you integrate any trigonometric function over one period, and it doesn't matter if there's a delta term right here, but if you do that, if you just think about the graph of any trig function, if you integrate it over one full period, you're going to get 0. Okay, so that cancels this whole term out. We don't have to worry about it. The next term here, you simply have 1/2 multiplied by cos of delta. Well, that is simply a constant that you can take outside of the integral, and now what you're left with is you're simply integrating dt. So that ends up giving you the period. Now at the end, you can cancel out that period with the 1 in the definition for the average, so that simplifies your life quite a bit. So this is my final expression for the average power. It has a factor of 1/2 that comes in, Imax multiplied by Vmax, and multiplied by cosine of this angle delta. Let's box this equation up. This is an important equation right here. All right, let's examine our equation right here. And we're going to start by looking at something called the power factor. And we're going to look at it at one specific frequency, and that frequency is called the resonant frequency. So what does that power factor look like, but only at one frequency, omega? Okay, first of all, this term called the power factor, the definition of that term is nothing more than this cosine of the delta. Okay, so somebody asks you what the power factor is, that's it. You're done. All right, next thing we have to do now is, well, let's define the power factor. What does it look like at this specific frequency, at our resonant frequency? Remember, at resonance, we have that the two reactance terms are equal to each other. The inductive reactance XL equals to the capacitive reactance XC for this series circuit. That means that the angular frequency that I drive at is going to be at some resonant frequency, some specific value. And if you look at this condition for the reactance values, it leads you to this resonant frequency of 1 divided by the square root of L times C. All right, let's go back to another definition we had for that angle delta when we looked at series AC circuits, something I did in the previous video. So I showed you that the tangent of that same angle delta can be written as this, the difference between the two. But if we're at resonance and we're using our resonant condition right here, imagine if you substitute that right up here. Right? What would that mean? Well, that would mean that these terms cancel out because they're the exact same thing. So we get 0 for that, okay? If you get 0 for the tangent of that angle delta, it means that the angle delta is itself equal to 0. So imagine now we go back and we substitute this 0 inside my average power definition. Cosine of that angle delta would be equal to 1 if the angle is 0. Okay? That means that at least at resonance is when we're going to have the maximum value of this power factor. Okay? So at resonance, if we have the maximum value of cos of delta up here, it means that our average power is itself going to be a maximum value. This is the most amount of power you can deliver from that AC source is when you have the angle delta equal to 0. Okay? You can't have any more power being delivered by the AC source. All right, I want to look a little bit more closely now at this average power expression. Let's write it now, everything in terms of the parameters of the circuit. So we start off with our cosine of delta. What you could do is just draw the phasor diagram for a generic series LRC circuit. You should get something that looks like this. We have the resistive term on the x-axis. We have combined both of the reactive terms on the y-axis. And then the voltage across the generator can be written like this. So using this diagram right here, what you end up doing is you write cosine of the angle delta as the adjacent over the hypotenuse. You can cancel out the Imax factors, and now you can go ahead now and substitute this cosine of delta back up here into my expression for the average power. All right, and this is what we get. Now the next thing I want to do is maybe eliminate Imax and also eliminate the value of this total impedance, because both of those we did in the previous video. Remember, Imax, you can simply write it as the maximum voltage of the generator divided by the total impedance of that circuit. And the total impedance, at least the square of it, you can write it like this. So now we're left with this expression here for the average power, which is written as Vmax squared multiplied by the resistance divided by 2 times this impedance squared. So let's go ahead and substitute everything in here for this impedance squared term. You get your final expression for the power that looks like this. Now this is all written in terms of the parameters of the circuit. R is the resistance, L is the inductance, C is the capacitance, and this is the equation we really want to look at. So if you made a sketch of this curve right here, so I'd be plotting the average power versus any value of omega that you substitute inside this expression over here. Omega only appears down here in the reactive terms. If you make a sketch of that, again, it'll depend on the different values of the parameters, but a generic sketch might look something like this. It typically has a peak function, and it could look symmetric or asymmetric depending on the values. I'll show you some specific values a little bit later on when we talk about the Q factor, but this is just a generic plot. It has a peak value, and the peak value is when we drive this circuit at the resonant frequency, which we've discussed before. And, well, the maximum value of the power is when you are at resonance, and that's when all of these reactive terms right here vanish. And that maximum power then is simply left with the resistive terms. So you're left with 1/2 Vmax squared divided by R. All right, the next thing I want to do now is look a little bit more closely at this curve, and I want to look at something called the full width at half maximum of this power resonant curve. So if I would go on this diagram here, if I define this as half power, if this is the max, the half power would appear somewhere right around here. This is when the power is P average, the maximum divided by 2. You can see there are 2 values of omega here where I obtain this average power is equal to half of its maximum value. So my goal now is going to be to calculate what are both of these frequencies here, omega, and define this full width at half maximum. You're going to find that the width of this curve right here depends a lot on the resistance of this circuit. The peak position, on the other hand, that depends solely on what is the resonant frequency of this circuit. Let me show you some examples of different power resonant curves now based on different values of parameters for circuits. All right, I want to look at a specific example here. So I have my series LRC circuit. Now I'm going to consider these values of the parameters here. So R is set to 200 ohms. The capacitance is 15 microfarad. The inductance, 230 millihenries, and my maximum applied voltage here is 36 volts. What I did here is I'm plotting this average power here on the y-axis and versus omega here on the x-axis. Again, and the equation that I'm plotting is shown right here. That's the one I previously derived. Now, a couple things about this circuit right here. You notice that, or this curve, it doesn't quite look like the sketch I did. Well, that's because in this case, the value of the resistance is kind of big. I'm going to show you some cases where I reduce this in just a minute. But nonetheless, it still has a peak, and the peak happens to be right here, and that is the resonant frequency of this circuit. This resonant frequency you can calculate as 1 over square root of LC. For this circuit here, it ends up being approximately 538 radians per second. All right, what else do we have? Well, we have a maximum, right? The maximum is right here. Again, that's when this reactance terms goes to 0. You substitute the numbers, you get approximately 3.24 watts is that maximum average power that I'm going to have being delivered to this circuit. All right, now what I want to do is let's have a look at what it looks like if I keep many of these parameters the same, but I'm simply going to reduce the resistance. I want to show you what happens to the curve. So I'm going to reduce it to 100 ohms, 50 ohms, and 25 ohms. And again, I'm still plotting the same function here, but have a look at the different curves. So here's what we have. So the blue curve is now kind of still down over here at the bottom. Right? It's the same curve I showed you on the previous slide, except now what I have is I have different values of the resistance, and the resistance are all getting smaller. So the red one here has a resistance of 25 ohms. What do you notice about those curves? First of all, one thing you should notice is that the peak values are all at the same values, okay? That's because, guess what? I haven't changed anything to do with that resonant frequency. It's still 1 over square root of L over C, and the only thing I'm changing is the resistance values. So we don't have to worry about that. Let me show you one other case where I'll make the resistance 10 ohms, and you're going to see this one. That's the purple line over here shown in this figure. Again, a very, very high peak. So I changed the maximum value. Remember that maximum value depended on the value of the resistance. So that's why that the maximum value shoots up very, very high. The other thing we notice is that the peak becomes more symmetric. Right? It looks like it's just kind of a nice, friendly function over here that is symmetric about that resonant frequency. So, how would I change the peak then of the resonant frequency? Well, then I have to change either the capacitance value or the inductance value. So let me show you another case now where I'll add another curve to this plot where I'm going to change the capacitance. And in this case, I'm going to make the capacitance twice as small. That is the brown line here that I'm showing in this figure. Here it's the exact same parameters as the purple line. Actually, let me get rid of that. That makes it hard to see, but you can see that both the purple and the brown line both have 10 ohm resistors. The only thing I've changed is I've changed the value of the capacitance. And for this brown curve, I've made the capacitance half the value of the capacitance for the purple curve. You can see now it shifts that resonant frequency to higher values of omega. Again, because that resonant frequency is equal to 1 divided by the square root of L over C. If I make C smaller, guess what? I'm dividing by a smaller number. I'm going to get a higher resonant frequency. You can see that the shape of the curve between the purple and the brown, they're very, very similar to each other. They're simply kind of shifted over here. All right, so in my next part of the video now, we're going to be interested in looking at, again, if this is the maximum power, if you go to half the value, how do I calculate these guys right here? What are these two frequencies where you get half the amount of power? And what is this width of this curve right here? This is something called the full width at half maximum, okay? FWHM. All right, I now want to show you how you calculate the full width at half maximum of this complicated expression over here. So the first thing we do is, well, remember that the maximum was simply Vmax squared divided by 2 times R. What you have to do now is I want to find when it's going to be equal to half that value. All right, so instead of 2 times R, I have 4 times R down here at the bottom. And my goal now is simply to solve this expression for which values of omega correspond to this equation being satisfied. All right, so that's not too bad. So what I have to do now is simply simplify some of the terms over here. So you can start by canceling out some of the terms that appear on both sides. For example, Vmax squared appears on both sides. I have a factor of 2 that I could factor out. I'm still left with this 2r on the right-hand side of the expression. The next thing you want to do now is simply rearrange this expression. So group all the r's on one side, get rid of this term on the denominator. All right, but anyway, we could start with this. So just clean it up a little bit. This is what we're left with. I brought the r over on the left-hand side over here. So you have r squared. And you want all of this simply equal to 1/2. Well, now we have to do a little bit of algebra. So we have to bring this whole term on the denominator over to the right-hand side. And if you multiply through by the 1/2, this is what you get. The next thing you do is you can combine both of these terms, this guy and this guy, right? We have 1, and here you have 1/2. So bring everything over to the right-hand side, and you're going to be left with 0 and minus 1/2 r squared, and then this complicated-looking expression over here. All right, we still have some work to do in order to simplify this, but again, the goal is simply to solve for what is the value of omega. Again, you can maybe just cross out the r values. That'll simplify your life a little bit. And then you're left with one final expression here that we're going to try to solve. Well, let's go on the next page and finish this off. All right, at this point, it really just is algebra. So we have to kind of manipulate this expression to try to solve for omega. The way that I like to do it is following kind of this approach here. I'm going to just work with terms inside this bracket over here. So I take out an omega just to get rid of this term in the numerator. And I bring out the value of L also. So that's what this looks like when you simplify. And you can see that this term inside the bracket, it starts looking like the resonant frequency. But again, everything here is squared. We can't forget about this. So let's square both of those terms in the front, the L over omega, and you bring that outside of the bracket. All right, next thing I want to do is maybe multiply through by omega squared and divide through by L squared just to get rid of this leading term right here. It's going to change the coefficient of the resistance squared term to look like this. All right, now what can we do? Well, we can introduce my resonant frequency and replace this term over here by the resonant frequency. And if I bring this term to the other side, this is what you're left with at the end. So again, the goal is to solve for omega squared. It appears in two places right here. It's kind of still a complicated expression, but let's just maybe take the square root of both sides. If I do that, you have to have two solutions over here if you take the square root. So I'll just include both of the solutions here over here on the left-hand side. And this is what we're left with. So this is a quadratic equation or two quadratic equations, and we're trying to solve for omega. So I'm going to show you how to do this on the next page, and we're going to make one approximation, so I'll discuss that on the next page. Okay, so this is what we're trying to solve for, right? Solve for omega. I'm going to call this right-hand side here, I'm going to call this some function of omega, f omega right here. And the goal now is you really want to, we want to approximate this curve near my resonant frequency. Okay, and I'm going to show you why in a minute, okay? So that's really what you want to do. I mean, you could solve this, it's a quadratic equation, but it just gets kind of messy. So what's typically done here is, if we look at cases where the resistance is small, okay? For example, right over here, when the resistance is only 10 ohms, you can see that it peaks very, very sharply. And the smaller the resistance, the higher the maximum power, and the sharper that peak right here. So this is going to be the approximation that we're going to do, is when the resistance is small. Now, if you look at both of these values, this is approximately the two values of omega that I'm trying to solve for. Both of these are actually pretty close to the omega, right? My omega was like 530 something, and you can see that both of those are at least, you know, within like maybe 40 or 50 radians per second from that peak value. Okay, so if we're dealing in this limit, this is what we're going to want to do, is suddenly approximate this function here and try to linearize it in order to make this calculation more simple. All right, so here's my function, f of omega, that I've defined. The way that you approximate this function near that resonant frequency is we define a Taylor expansion. The Taylor expansion of f of omega, the approximate value, maybe I should have a squiggly line here, it says, well, it's the value of the function at that resonant frequency plus the first derivative of that function evaluated at that resonant frequency multiplied by a linear term, and plus some higher order terms. So we're not going to include these higher order terms here in this calculation, but we have to evaluate all of these. So let's start with this guy. If you substitute omega equals to omega res, clearly what you get is 0 right here. All right, you just substitute that into this expression right here. The next thing we need to know is evaluate the derivative of f with respect to omega, and then substitute omega equals to omega res in that equation. What you do now, that's very easy to take the derivative. It's simply 2 omega, and then you substitute omega equals to omega res, and you're left with this. So this is the approximation that we're going to do. And therefore, what you do now is simply substitute f of omega by this linearized expression. Instead of solving something for omega squared, we simply have to solve now 2 terms that have omega in it. And again, this is true when omega is kind of near omega res. When does that happen? That happens when the resistance is small. All right, so now let's go on the next page and just finish off this calculation here. But we're basically now just solving this equation right here, which is linear in omega, rather than solving this more complicated quadratic equation for omega. All right, time for some more algebra. Again, this is just solving for omega, so just take your time with the algebra. It's not too bad. Just start by multiplying through and maybe group together all the terms with omega on the left-hand side. If I do that, I'm going to have 2 terms. There's the 2 times omega res term, and then there's this term here, which was originally on the right-hand side. I bring over to the other side. Both of those multiply omega. All the other terms are simply the 2 omega resonant squared terms that I get from multiplying up here. All right, next thing you want to do now is get omega by itself, or I guess you could divide through by 2. Let's just simplify this. Get rid of the 2's everywhere. That introduces a 2 in the denominator over here for that second term. And now what we're left with is just get omega by itself. So you have to divide through by this entire bracket. Okay, and this is what it looks like. You could kind of, again, this is the answer. If you wanted to, you could write this in a slightly different form. What you could do is maybe factor out a resonant frequency from this denominator term. Take that out, and then you can cancel one of them out because you have squared in the numerator and 1 term in the denominator. Get rid of that. All right, and then you're left with my final expression here for the 2 values of omega that correspond to the full width at half maximum. Okay, so that's it. This is what you're left with. And you can multiply through omega res. It'll cancel out with this guy here down at the bottom. And that's it. These are the 2 values that we want for our values that correspond to where you get the full width at half maximum of this average power function that we have. So now let's go back on a graph and define both of those. And the important thing right here is that these values, they depend on this resistance right here. So when you make that resistance small, the omega values that you get, right, this whole term here, the second term, this correction term, would end up being small. So the omegas that you get are close to omega resonance, which is what we wanted in the first place. It also depends on the inductance right here. All right, so this is what it looks like, right? We have our average power curve for some values, parameter values. We have a peak that happens at this omega frequency, which is the resonant frequency of the circuit. What we've looked at now is for which values of omega do we have the power equal to half the maximum power. So that is right here. And what we found here were 2 values. So one value corresponds to this guy. This is when omega equals to omega res plus r over 2L. And this other guy right here is when the frequency is omega resonance minus r over 2L. This is what you define as the full width of the curve at half maximum. It's defined in terms of the power, okay? And now this width, you can see it has a certain width, which sometimes you call delta omega, okay? And that width, delta omega, for this LRC circuit here, again, if you just take the difference between the positive and the negative solution, you're simply left with r over L. Okay, so this is an important parameter that describes the width of that curve. kind of is related to how much damping there is, right? You could see that the bigger the resistance value is for an LRC circuit, the wider this curve is going to be. And we saw that when I had, for example, the 200 ohm resistance versus the 10 ohm resistance. You had a much broader curve in the case of 200 ohms. All right, so now we're in a position where we can define something called the Q factor, or the quality factor for a resonant harmonic oscillator. All right, now I want to define something called a quality factor. It's a number that's often used to describe power resonant curves. And this is the definition. It's 2 pi multiplied by the maximum energy stored in a harmonic oscillator divided by how much energy is lost per cycle of a harmonic oscillator. So if we think about an LRC circuit, you could think about the maximum energy stored as either the maximum energy stored in the inductor or the capacitor. And in terms of energy loss, you can think of that being as the power multiplied by the time for one cycle. So think about the resistance and the resistive losses in an LRC circuit. So I'm going to substitute my values here. For maximum energy stored, I would look at, for example, the inductor, 1/2 Li max squared. That would be the maximum energy that you would store in a harmonic oscillator circuit like this. For the energy lost per cycle, again, I've just got this now as the energy being dissipated by that resistor, the average, and multiplied by the period, because I just want to know the energy here in one cycle, not the power. So now you can cancel out quite a few things, and you're left with this expression right here, which is 2 pi divided by the period, multiplied by this ratio, L over R again. So you can see this is coming out. The 2 pi divided by the period, I can replace that by that resonant frequency, right, approximately, and multiplied by L over R. The next thing we do is in the limit when R is small, we had that you can write this ratio of L over R in terms of that full width at half maximum, right? That was something we call that delta omega value, which was defined as the full width at half maximum of that power resonant curve. So at the end, this Q factor is simply related to this width, and this is how you can write this expression for the Q factor of a harmonic oscillator, right? Again, this is an approximate solution because we are assuming here that R is small and that curve is symmetric and kind of look like some of the curves I showed you before, for example, when the resistance was 10 ohms. So let's have a look now at the quality factor for some of those previous curves that I showed you. Again, you just substitute one value of the resonant frequency here, and then you divide by delta omega, which was simply L over R, or R over L rather. All right, so this is what it looks like at the end. Again, I have 5 of these curves here shown for different value of the resistance values, right? 200, 100, 50, 25, and 10. And I've calculated in each case that quality factor for each one. Okay, again, I've used this approximate definition here for that quality factor, the resonant frequency divided by that delta omega. So when R is small, have a look. When R is small, I have the purple curve. That quality factor here gave me a number of 12.4. You can see that, when you're certainly above like 2 or 3 for the quality factor, you have kind of a nice symmetric curve. When the quality factor is small, like 0.6 or 1, the curve is very asymmetric. Okay, so this definition probably is not that accurate when that curve is broad for the full width at half maximum. But what you're looking at is for large values of Q correspond to small value of the resistance, and small values of Q correspond to large values of the resistance. So any harmonic oscillator can be characterized in terms of its full width at half maximum. It can also be defined in terms of this quality factor, which is often used. All right, hopefully this is a good introduction to quality factor and power resonant curves for you. You're ready to tackle some problems now.